Welcome back to our deep dive series. Today we're revisiting the online encyclopedia of integer sequences, the OEIS.
A fantastic resource. Always something interesting there.
Absolutely. And for anyone studying number theory, it's just invaluable. We're continuing our exploration of some, well, really captivating sequences within it.
Mm-hmm. It's amazing what pops up.
Today our focus is OEIS sequence A000218. The title is pretty descriptive. Sum of squares digits.
Right. The definition is quite straightforward.
Yeah. You just take the previous number in the sequence, you square each of its digits individually, and then you sum those squares up. That result is the next term.
And for this specific sequence, either 0, 0, 0, 2, and 8, the starting point is 3.
Exactly, starting with 3.
Yeah.
So let's trace it out a bit. We start at 3.
Okay.
Square the digit 3, you get 9. Simple.
Next term is 9.
Then square the digit 9, you get 81.
Right. Now it has 2 digits.
So for 81, we do 8 squared, which is 64, plus 1 squared, which is 1.
64 plus 1 is 65.
Next term, 65. Okay, now 6 squared is 36, 5 squared is 25.
Yeah.
Add them.
36 and 25, that's 61.
Okay, 61. So 6 squared is 36 again, plus 1 squared is 1. That gives us 37.
37.
Now from 37, let's see, 3 squared is 9, 7 squared is 49, 9 plus 49 is 58.
58. Then 5 squared plus 8 squared, 25 plus 64, that's 89.
Getting bigger numbers now. 89, 8 squared is 64, 9 squared is 81. Add them.
64 and 81, 145. 3 digits now.
Okay, 145. 1 squared is 1, 4 squared is 16, 5 squared is 25. So 1 plus 16 plus 25.
That's 42.
42. Then 4 squared is 16, 2 squared is 4, 16 plus 4 is 20.
20. Okay, nearly there. 2 squared is 4, 0 squared is 0.
So
4.
Then 4 squared is 16.
16. And
Yeah.
from 16, 1 squared is 1, 6 squared is 36. 1 plus 36 is?
37. And hang on, 37, we've seen that before.
Exactly. We're back to 37.
So it looks like it repeats from there.
It does. That's a key feature. The OEIS entry itself, in the hints, mentions this could be seen as the orbit of 3 under another sequence, A003132, which is just the operation itself summing the squares of the digits.
So the orbit is just the set of numbers you hit by applying the rule over and over.
Precisely. And the formulaception explicitly states the sequence becomes periodic, eventually periodic, with a period of 8.
Okay, so after those first few terms, 3, 9, 81, 65, 61, we land on 37.
And then it cycles.
Right, the cycle is 37, 58, 89, 145, 42, 24, 16, and then back to 37, an 8-number loop.
It's a classic example of how iterating a function can lead to these stable cycles. It's not random.
So the big question then, the core of this deep dive, is what can we really learn from this? It seems so simple. You know, square the digits, add them up, what's going on underneath?
Well, it turns out this isn't just a quirk of starting with 3. That cycle is fundamental. We looked at a square digit sum article,
Right.
and it confirms what the OEIS hints at. If you start with any positive integer and you keep applying the sum of squares of digits rule,
Any number.
any positive integer, you'll eventually end up in one of 2 places. Either you hit the number 1,
Okay.
or you fall into that exact cycle we just found, 4, 16, 37, 58, 89, 145, 42, 20, and then back to 4.
Wow. So it's either one or that specific loop, nothing else.
Nothing else. It's quite a powerful result. And it's not new, actually. The article points to a 1945 paper by Arthur Porgis.
1945, so this has been known for a while.
Oh, yes. In the American Mathematical Monthly, his paper was titled A Set of 8 Numbers, referring to that very cycle. He proved this general behavior.
That gives it some serious mathematical weight then. It's not just recreational math.
Not at all. Porges showed why these paths, these sequences, are ultimately constrained. They can't just wander anywhere.
Which ties into this idea of happy numbers, right? We saw that on Wikipedia.
Exactly. A happy number is simply a starting number that, under this process, eventually reaches 1.
And if it doesn't reach 1, it must fall into that cycle.
Correct. Those are called sad, or maybe more commonly unhappy numbers.
So our sequence A000218, starting with 3, since it ends up in the cycle and never hits 1,
3 is an unhappy number.
it's a neat way to classify them. Happy versus unhappy. It really highlights this fundamental split.
It does, and we can generalize this a bit too. There's a paper, Iterations of Sum of Powers of Digits.
So not just squares, but maybe cubes or fourth powers.
Exactly. It looks at summing the kth powers of digits. For our case, KO to 2 sum of squares. The paper shows that for 2k, you get fixed points, like 1.
Because 1 squared is 1, so it stays there.
Right, and you get limit cycles, like our 8-number cycle. That's a limit cycle.
Okay, that makes sense. But why does it have to end up in either a fixed point or a cycle? Why can't it just keep going, generating new numbers forever?
Well, there's a crucial lemma in that iterations paper, lemma 1. It basically says If a number dollars is large enough specifically, if it has k plus 202 plus or more digits.
So for us, k plus a 2 if that means 4 or more digits.
Right. If a number has 4 or more digits, then that number on the roll is always bigger than the sum of the squares of its digits, 2 on ours.
Always. So any number with 4 or more digits, when you apply the rule, the result will be smaller.
Guaranteed, it has to decrease. Think about it. The largest possible sum of squares for a 4-digit number is for 9999. That's 4 times 81, which is 324.
Much smaller than 99999.
Exactly. So no matter how big a number you start with, if it has 4 or more digits, applying the rule shrinks it. Eventually, you must fall below 1,000.
Okay, I see. So you can't just keep getting bigger and bigger numbers indefinitely. You're forced into the realm of 1, 2, or 3-digit numbers.
Precisely. And since there's only a finite number of integers below 1,000, specifically 999 of them, the sequence must eventually repeat a value it's already visited.
And once it repeats a value.
It's caught in a cycle. Or it could land on 1, which is a fixed point, a cycle of length 1, if you like.
That's really elegant. The process forces the numbers down until they get trapped.
It is. And another paper we saw from the IJCDM journal specifically looked at k over 2 and confirmed this. It stated that if the sequence doesn't end up at 1...
And we'll eventually enter that 4, 16, 37 cycle.
Exactly. It perfectly matches the OEIS sequence A000218's behavior after those initial terms. The consistency across different sources is quite strong.
It really builds confidence in the result. Now, something else got my eye in the comments for the square digit sum article. They mentioned different bases, like base 16 or base 8.
Ah, yes. The behavior is base dependent. If you write numbers in, say, hexadecimal, and apply the same rule, square the digits, which might be A, B, C, and sum them, you generally get different fixed points in different cycles.
So this happy number idea and this specific 8-number cycle are kind of artifacts of our base 10 system.
In a way, yes. The specific outcomes depend on the representation. Exploring different bases opens up a whole other area.
Fascinating. And just to connect this back to something more computational, we saw a couple of YouTube videos showing code.
Right, programming examples. How to actually compute the sum of squares of digits in Java or Python.
Yeah, from Coder Bano and TS Info Technologies.
Yeah.
It's neat to see how you'd actually implement this to test numbers or explore the sequences yourself.
It's a good reminder that these abstract concepts can be explored computationally. You could write a quick program to check if a number is happy or unhappy or trace its path.
Definitely. So, wrapping up this look at A000218, the big takeaway seems to be this incredibly simple rule, summing squares of digits, leads to this surprisingly structured outcome.
Absolutely. Every starting number has a predetermined fate. Either it reaches 1, becoming happy, or it inevitably gets drawn into that single 8-number cycle, making it unhappy.
And our sequence, A000218, starting from 3, is a clear demonstration of landing in that unhappy cycle. 37, 58, 89, 145, 42, 24, 16.
It settles right into it.
It really makes you wonder, doesn't it? You look at the OEIS, see all these sequences based on digit manipulations.
Yeah.
What other kinds of patterns are hiding there?
Yeah, how much does changing the base, the very way we write numbers, alter those patterns?
Yeah. This dive into A000218, it feels like just scratching the surface of the patterns hidden in basic arithmetic. Definitely something to think more about.